Assalamu alaikum. Hello, everyone. My name is Bاشmاخ. I am a senior computer science student, and I'm here today to talk about cryptography, a topic that I love. So today we'll go over the field of cryptology. We will go over the basics of symmetric cryptography. We will visit an example of symmetric cryptography, which is the substitution cipher. We will view some cryptanalysis attacks, and we will go over the basics of asymmetric cryptography. Okay, so starting with the question, what is cryptography? So you might be surprised to know that the general term is actually cryptology. And then under cryptology, you have two main branches, cryptography and cryptanalysis. Can anyone guess what's the difference between cryptography and cryptanalysis? Okay. Okay, the question is, can you guess what's the difference between cryptography and cryptanalysis? Okay, I got some interesting answers. One got it right. So actually, cryptography is a way of writing with a goal to hide the original message, whereas cryptanalysis is known to be an art of breaking crypto systems. Okay, under cryptography, we have symmetric ciphers, asymmetric ciphers, and then protocols, which are just the application of symmetric and asymmetric ciphers. Okay, so starting with the setup of symmetric cryptography, we have Alice trying to communicate with Bob over an insecure channel. And the problem starts when there's a third person, usually referred to as Oscar, trying to hear whatever Alice is saying to Bob. And how do we solve this? Well, we add an encryption function in Alice's side, and then a decryption function in Bob's side. So basically, when Alice sends a message, for example, if Alice sent hello, this is the plain text, the original message, and then after it goes into the encryption function, you get a scrambled set of characters. If we get XY, GCF, for example, and then luckily, this is the text that everyone here can see in the insecure channel. And after the message gets to the decryption function in Bob's side, Bob gets the original message back. As you can see, our problem now is solved. Alice and Bob can see the original message, while everyone else in the middle can only see a scramble message. Okay, I have a question for you. Do you think we should keep these algorithms secret or public? Okay. Okay, we got like 50% secret, 50% public. That is interesting. Well, actually, the only way to know that an algorithm is secure is to have it public and have people attack it. That's the only way we could ensure the security of the algorithm. But then in addition to the setup we have here, we have something that should be kept private. And that is our secret key. The key should be the only thing to be kept private in a crypto system, whereas all the other encryption algorithms, decryption algorithms should be actually kept public. Okay, so X here is our plain text, our original message that is in readable format. And then after going to the encryption function, you have Y, the ciphertext, the scrambled set, random set of characters. And then you have K, your secret key. This key should only be accessible to Alice and Bob. And this should be, they should transfer this over a secure channel, maybe a guy on the mail. Okay, so going to substitution cipher, which is an excellent way to show how symmetric cryptography works. Substitution cipher is a historical cipher, which is just a polite way of saying it's old and stupid. No one today uses substitution cipher. The substitution cipher encrypts letters rather than bits, so it operates on the actual text rather than the digital representation of it. All modern cryptography operate on bits. So the idea is to replace each plain text letter by a fixed other letter. And so if you have, for example, here, this is our key. For every A in our plain text, we'll replace this with a K in the ciphertext. And then for every B in the plain text, we replace with D, and so on for all the letters of the alphabet. And question, if we have the text ABBA, what do you think it would look like after encryption? Yes, everyone got it right. We're gonna have KDDK. And then now you can see when we want to decrypt this, we're just gonna reverse the process and get our plain text back. Okay, question. Do you think the substitution cipher is secure? Okay, everyone got this right. Okay, we'll see. We will now try some attacks against the substitution cipher. Okay, starting with the first type of attack, we're going to try a brute force attack. And basically the idea of brute force is to try for A, all the possible letters in the alphabet. And then for B, we're going to try all the possible alphabets. But when we put a ciphertext letter for A, we cannot reuse the same letter. So for A, we're going to have 26 possibilities. And then for B, since we crossed one out, we're going to have 25 possibilities. And then how many possibilities are we going to have for C? Yes, 24. Yes, we're going to have 24. So simply try every possible substitution table, which is our key, until a text that makes sense appears. Whenever we find a text that is in readable format, we're going to assume we found our key. But there's a problem. How many substitution tables do we have? Well, we have 26 factorial. We've seen that we have 26 possibilities for A and then 25 possibilities for B and so on. And so this is almost equal to 2 to the power of 88. This is a huge number. And so the search for 2 to the power of 88 keys is completely impossible, even with today's computers. Okay, since we can now conclude a brute force attack is practically impossible with the substitution cipher, can we now conclude that the substitution cipher is secure? Yes, not yet. Yeah, exactly. Okay, so going on to the second type of attack, we're going to perform a letter frequency analysis. And the basic idea of a letter frequency analysis is that in any English text, you're going to have varying frequencies for different letters. An example of this would be when you play hangman, and then there's a set of letters you choose right at the beginning, because you see these letters a lot. And so this is the idea that is used in letter frequency analysis. Whatever letter you see a lot appearing in the ciphertext, you're going to assume it's one of these. So letters have different frequencies in the English language, and the frequency of plain text letters is preserved in the ciphertext. This is why it works, because if you see the letter K a lot in the ciphertext, this also means that the letter A will appear a lot in the plain text. It still holds. For instance, E, as you can see here, E is the most common letter in the English language, in any English text, followed by T. And then you have here some letters that are very infrequent. Okay, now you can see that even though a brute force was not successful, okay, if you have this ciphertext here, for example, can you guess what's the most occurring letter in here? Yes, it's the letter Q. It appears 10 times in this text. Okay, and since we know E is the most occurring letter in any English text, we can now replace every Q with an E. And then, for example, if you see this, can you guess what this word is? Notice that E is in the original plain text, but R and D are still ciphertext. So we need to replace R and D with some letters. Yeah, so this word is probably the, since it's something, something, and then E. It's a three-word letter, and as you can see, it occurs more than once in the text. So you could guess this is the. And then after further guessing based on the frequency of the remaining letters, you can get your original plain text back. Okay, as you saw, we could not perform a successful brute force attack, but we successfully performed a letter frequency analysis. We could break the code. So this is an excellent example that any encryption scheme must withstand all types of attacks. The advantage for a hacker is that only one of your attacks should be successful. But as a crypto system designer, you're a bit in a bad spot because you must ensure your system must withstand all types of attacks, especially that there are new attacks emerging every day. Okay, now why do we need cryptanalysis? Well, because there is no mathematical proof of security for any practical cipher. For example, if I were to give you an encryption function here right now and ask you if it's secure, there's no way you could give me an answer, which is probably the reason why I can't see any hackathons or competitions for making new ciphers. They really cannot announce a winner. And the only way to have assurance that a cipher is secure is to try to break it and fail. You have to put it in public, have others attack it, and then if no one could attack it for many years, only then you could assume it's secure. This thing for cryptography does not hold in any other engineering discipline. If you were, for example, an engineer trying to make a car that runs low on gas, you could make your car and then test it, and then you could tell if you succeeded or not. For cryptography, it's different. You can make an algorithm, but you can't be sure it's secure. And then in cryptography, we have Kirchhoff's principle. A crypto system should be secure even if the attacker knows all the details about the system, like the encryption and decryption algorithms, with the exception of the secret key. So the secret key is the only thing that you need to have private. Okay, so going on to the classification of cryptanalysis. First, we have a class of classical cryptanalysis, which are the types that we tried earlier. We performed a brute force attack and then a letter frequency attack, which is a form of an analytical attack, or we could also call this a mathematical attack. And then we have social engineering. And the classical example of this would be, hello, this is your IT department. We urgently need your password to update your account. And surprisingly, many people fall to this. And then we have implementation attacks. And for implementation attacks, if you know your credit card, your bank credit card, it has a small, tiny computer. It's an 8-bit computer, and you can see it in the gold chip. And so you have, this is your card, and then you have here your small computer. And then somewhere in the memory, you have your key hidden. And so what these people do is that they bring an oscilloscope. They plug it to this computer, and they basically act like an ATM machine. They trigger the algorithm, they tell it to encrypt. And when it runs, they record the power trace of the processor. And since the processor and the key have something in relation, they can use this power trace and apply some signal processing to figure out the key. Now, of course, modern banks have ways to protect against this attack. Okay, so now going to my favorite topic, which is asymmetric cryptography. So in order to understand asymmetric cryptography, we will revisit the basics of symmetric cryptography. So for symmetric cryptography, for example, if you have your message hello, and then you apply your secret key to encrypt it, you get this ciphertext or this random set of characters, and then you apply the same key to decrypt and get your original message back. For asymmetric cryptography, things are a bit different. You have your original plain text, and then you use your public key. And this key is, as it says, it's public. You can put this on your website, on your email. You want people to use this. So you have your original text, and then anyone can encrypt this using your public key. And they get the ciphertext, which they send to you, and then only you have access to your private key. So only you can decrypt the message and get it back, but anyone can encrypt messages to you and send them as a ciphertext. So asymmetric cryptography is relatively new. It was introduced in 1976. It is based on the principle of a mathematical one-way function, where it's easy to compute it one way, but practically infeasible to do it the other way. Asymmetric cryptography is mainly used for key establishment, for example, for symmetric cryptography, and then for non-repudiation to hold people accountable, it's like a digital signature, and for identification and encryption. Most practical protocols are hybrid protocols, which incorporate both symmetric and public key algorithms to get the best of both. So as a summary, we went through the field of cryptology. We visited cryptography and some of its types like symmetric ciphers and asymmetric ciphers. We also went through cryptanalysis. We applied some classical cryptanalysis. We saw an example of social engineering and implementation attacks. Thank you for listening. I hope you enjoyed, and I am happy to answer any questions.
Thank you, Asma. We have some questions here we're going to answer. So there's an attendee who's asking, what are some real-life examples of where is cryptography is used?
Okay, well, in like until like the 1970s, cryptography was only used in governmental things, but currently it's being used everywhere. And the first public mass application of cryptography is when you talk on the phone, the voice over IP. This is the first place where cryptography was applied.
Okay, we'll go to the next question. Is it possible that a type of cryptography that can never be hacked or cryptanalyzed?
Well, the substitution cipher was once considered secure, but then it's always emerging. So for every year, you have hundreds of publications over cryptology and its applications. And so a crypto system that is considered secure today might not be secure tomorrow.
That's right. Thank you, Asma. Do you have any other questions, guys? Asma, I have a question for you. Do you have any recommended websites for like enciphering text or something?
Yes, I have a website. I'm going to send the link.
Okay. May you show us like a demo of how we can use it?
Okay, 1 minute. Okay, so here we have a type of an algorithm, which is the XOR. This is a symmetric cipher. And here you can choose your key. For example, if I have 1, and I have my plain text as hello, and you can see this is my encrypted text. And so if I reverse and I put the encryption here, I get my plain text back.
We have another question here. Do you have any books that you would recommend for cryptography?
Yes, the book that I used to study, which is Understanding Cryptography.
Okay, I'll just type the name of the book. May you repeat it?
Understanding Cryptography.
Thank you, Asma. I really enjoyed this webinar. I really hope that if anyone wants to ask you questions, they can contact you. If you want to drop any social media you want.
Yes, of course. Where can I end?
Yes, you can just drop it by the chat.
Okay. Okay, this is my Twitter here.
Thank you, Asma. I hope everyone enjoyed this webinar. If you have any questions, you can ask now. anything else, you can also contact Asma by Twitter, or and we will update you by our Twitter, CSC_club. Any updates about Cybersecurity Club, anything about cybersecurity, we're going to post there. Stay tuned.
Thank you, everyone.
الله يعافيك راندي. ولا تنسوا بعد رابط الحضور رسلنا بالشات ورابط التقييم بعد. فدام الحين خلصنا المحاضرة تقدروا تكتبوا آراءكم وإيش حابين تشوفوا بعدين وتستلموا شهايدكم. يعطيكم العافية، مع السلامة.